All right, let's settle down and get going today. And before I get into it, last reminder about the third exam review. No, wrong button. One of these days I'll learn how to use my tablet. All right, there we go. All right, so last reminder about the exam review, which is for the third midterm, going to be this Friday, 2 days from now. So that's April 19th, 1 to 3, probably not 3 p.m., but close to 3 p.m. usually is when we're done in this room. All right, so you're welcome to come to that. It will be recorded and put on YouTube like usual, so if you can't come or need to leave early or anything like that, you'll be all set. And then exam, as you know, starts on Monday, so that'd be the 22nd. I'll get ready for that. So just as a reminder, we're going to... The third exam doesn't go all of Chapter 9, so it basically covers about half of it through what we covered last time. So the structures of metals is kind of the last topic, major topic that's going to be part of that exam. The one last thing that I want to wrap up, though, that's related to the third midterm is how to classify the different types of solids. So we've kind of been going through a lot of these one by one and talking about them in varying levels of detail. We're going to get the last one sort of covered today, which is ionic solids. But we also want to be able to classify them, so distinguish them from each other if we know the formula of the substance or some other properties of that substance. How do we decide what kind of solid it is? So there's 4 major classifications, and the one that we've talked about in the most detail is metallic solids. And so when you're identifying these different types of solids, you basically want to look at the components, what makes them up, to be able to decide what kind they are. The other types that we worked on were a network solid, or more appropriately, a network covalent solid. We talked just a little tiny bit at the beginning about molecular solids, so we'll see some of their features in this table that are kind of important to consider, but not talk a lot about them in detail. And then the last one is our ionic solids, which, as I said, on this exam, you want to be able to identify what an ionic solid is and maybe some of the basic properties of it. The structural aspects of ionic compounds, which we're covering today, will not be on the third midterm. It will be only on the final exam. All right, but these are the 4 types of solids. And the first thing to think about, again, is what are the components of these? How do we identify what they are based on the formula of the compound or the substance? So obviously, as the name implies, metallic solids only contain metal atoms. So those are going to be the lattice points in a metallic solid would be, as we talked about last time, metal atoms located at different positions on those cubic or hexagonal structures, or those are the ones at least that we're going to deal with in this course. For a network covalent solid, these are also extended sort of crystalline solids, and the lattice points in this case are non-metal atoms. And we saw at the end of last time that there's 2 types of network covalent compound or network covalent solids. There's going to be atomic covalent solids, which are just one type of element, so the 2 forms of carbon we talked about, or silicon, which are just a single element that are linked together through covalent bonds. That would be considered a network solid, as well as the one example of a network covalent compound, which was SiO2, which is 2 different elements, again linked in these sort of infinite covalent arrays. But in those cases, the lattice points are the non-metal atoms that make up that particular structure. Molecular solids is the ones that we're going to, as I said, have the less detail about, but in this case, the lattice components are actual discrete molecules. So if we take a covalent compound that is made up of molecules, like water or something like I2, diatomic molecule, for example, and if we condense that into the solid phase, the solid that results is called a molecular solid, where each of the lattice points is a distinct molecule of that substance. And then finally, the one we'll talk about today, which is ionic solids, the lattice components are the different ions that make up the compound. So those are the components of these, and then you're kind of using this column here, what the lattice components, and then you can identify them based on that. So if we want to know if something is a metallic solid, we look at the formula of the substance, and a metallic solid just has one type of metal in the formula. So basically, all metallic solids are, for our purposes, elements. You would have, sodium is a metallic solid, or Gold is a metallic solid. Iron, anything that's a metal on the periodic table will be classified as a metallic solid when it's in the solid state. There are also alloys that are metallic solids, but we're not going to talk about those in this because alloys are basically mixtures of two metals in the same solid. But we're only going to talk about sort of pure metallic solids that made up of one element. Network covalent solids, they have, in the formula, they're only going to have nonmetals. So because these are covalent compounds, they're of course only made up of nonmetals. There can be either one or two different nonmetals in the formula. So they can be, as we said, atomic network solids, which just have one element, like carbon and silicon, or there are just the one example that we learned about of a network covalent compound. Molecular solids also consist of nonmetals, but these are ones that exist as molecules, like I said, water or all the polyatomic elements. But that's the case there. And then ionic solids, as we've been learning really since the very beginning of this course, an ionic compound consists of a metal plus a nonmetal. So any ionic compound would be classified as an ionic solid as well in sort of its structural, from a structural standpoint. So those are how you sort of look at the formula of these different things and decide, at least start to narrow down what type of solid it is. Another important factor to think about for these different solids is because they're condensed phases, because they're solids, there's going to be some sort of forces holding the atoms and molecules together. So whatever these lattice components are in the second column here, there has to be some type of force holding them together into that regular sort of rigid solid array. And what are those? Those are going to differ between these different types of solids. So if we think about metallic solids, we learned that the forces holding metallic solids together are metallic bonds. And that's that sort of third type of bonding we recently introduced that involves delocalized sea of electrons, as we called it. All right, so it's that delocalized bonding where the electrons, the valence electrons in particular, are delocalized over the entire piece of the metal. And that's what holds the metal atoms together into those solid structures that we talked about last time. In a network covalent solid, the only important forces involved in holding the atoms together are covalent bonds. So as we said, you have in a network solid sort of an infinite array of covalent bonds. It's not a discrete molecule anymore. It's sort of a molecule that goes on and on and on in all directions. And you have these covalent bonds that are holding the individual atoms in place, whether it be an element or a compound that's classified as a network covalent solid. For molecular solids, it's a little bit different. So we have covalent bonds that hold the molecules together. Those are the intramolecular forces. But then the only thing that's holding the molecules in place in the crystal would be the intermolecular forces. So these are going to be intermolecular forces like dispersion forces if it's a nonpolar molecule, or dipole-dipole forces if it's a polar molecule, or hydrogen bonds if it's something with OH or NH bonds in particular. So in a molecular solid, you don't have any sort of bonding interactions between the molecules. You just have bonds that hold the individual molecules together, but then those are held in the solid by intermolecular forces. And then finally, in ionic solids, as we're likely already aware, the main forces involved in holding these together are ionic bonds. All right, and then finally, I'll give you a few examples of these, because as I said, one of the things you're going to have to be able to do is look at the formula of a substance and decide which of these four categories does it fall into. So the ones that are metallic solids, as we already talked about, are basically any of the metallic elements. So sodium, iron, lead, any metallic element, which we know from the periodic table are the ones that occur on the left side, any metallic element would be classified as a metallic solid, and that's as simple as it gets. For the next two categories, network covalent solid and molecular solids, it's not terribly easy from just the formula of the compound to predict which one of those is going to be, because as we said, they're both just made up of nonmetals, and there's no real easy prediction for that. So really the way you want to do this is remember which of the few substances we know about are network covalent solids, and basically any other combination of nonmetals you would expect to be a molecular solid. Okay, so for network covalent solids, as we talked about, the two forms of carbon, graphite and diamond, which are both just pure carbon, those are examples of network atomic solids with just one type of atom in them. The elements that come directly below carbon on the periodic table, silicon and germanium, so basically all the group 4 elements that are not metals, so the group 4 elements that are either nonmetals or metalloids, those would all be classified as well as network solids. And those silicon and germanium especially are the ones that exist as semiconductors, another sort of factor we talked about last time. And then the only network covalent compound that you need to be familiar with is SiO2. All right, there are others, but that's the most common one and the only one that we would expect you to be able to identify. And then for molecular solids, it's basically any other covalent compound where it exists as discrete molecules. So any of the polyatomic elements that we talked about, so iodine, P4, S8, those are all solids in their standard state. Or if we take a gas phase element like Cl2 and we cool it down until it forms a solid, any of those will be classified as molecular solids. So again, they have the discrete molecules that make up the lattice points, and they're arranged into a regular solid array. And then there's a lot of compounds that would exist as well. So for example, ice, if we freeze water, we have water molecules that make up that structure, and those water molecules will be held together by hydrogen bonding in that frozen structure. So basically any covalent compound that exists as a molecule, once it's cooled down into its solid phase, it will be classified as a molecular solid. And then finally, the ionic solids is any ionic compound, which we've been talking about a lot in this course. So sodium chloride, magnesium oxide, MgCl2, etc. Whether it's binary or not, whether it's binary ionic compound or ionic compound with polyatomic ions, any of those will be classified as ionic solids. So most of these, the first and the last, are pretty easy to identify because the first one is just metals, the last one is just any ionic compound. These two in the middle, you especially want to be aware of which few of these are classified as network covalent solids and would have that sort of infinite three-dimensional bonding that's involved in those types of substances. So any questions on this? Because this, again, is the last thing we need to know for midterm 3, is how to classify these materials. So any questions on that before I move on to the new stuff? All right, so everything else that follows today will only be covered on the final exam. So you'll still need to know it, so you can't just zone out or leave. But not yet. You'll need to know it in 2 weeks, not next week. All right, so we're going to talk today about ionic solids in more detail. So we should be able to classify them based on what I talked about in the last slide. But we're going to talk now in detail more about their structures. All right, so for ionic solids, as we kind of already mentioned, there are forces of attraction between the ions that hold everything together. And we've talked about this in many different contexts in this course. First, when we introduced ionic bonding in Chapter 3, and then when we came back to talk about lattice energy in Chapter 7. All of that involves these forces of attraction between oppositely charged ions. So in an ionic structure, the ions are held together, held in place, by these strong forces of attraction between oppositely charged ions. Anytime you have a force involving charged particles, that can sometimes be called an electrostatic force. These are electrostatic forces of attraction. And of course, it's the opposite charges that are attracted to each other and that are holding things in place. So we're going to talk about a few different structure types that exist for ionic compounds. How exactly do these ions arrange themselves? And what they're essentially trying to do, and this is what really you're trying to do in any of these types of structures, is you want to maximize the attractions while minimizing repulsions. Because you have these attractive forces involving the oppositely charged ions, but if you put two ions of the same charge close enough together, they're going to start repelling each other. So what you want to be able to do is arrange the ions in such a way that you have the maximum forces of attraction and the minimum repulsions. Okay? And so that's how it sort of decides what structure it's going to take up. So the structures that we observe are going to maximize attractive interactions while minimizing repulsive interactions. Right? So there are a lot of different ionic structures, and that's really the whole name of the game. Put the ions in such a place that the attractive forces are maximized, and then the repulsive forces are minimized. All right. So when we have an ionic structure, then we have two different ions. We're only going to be talking about the structures of binary ionic compounds. Those are ionic compounds that just have two elements in them. And so one of the ions is going to be larger, one of the ions is going to be smaller. We learned trends for ionic radius also way back in Chapter 3. And typically the larger ion is the negative ion. As we said, when you add electrons to something, it gets bigger. So in most ionic structures, the larger of the two ions is the negatively charged one. Although that doesn't necessarily have to be the case, but it's usually the negatively charged ions are larger. And whatever the larger ion is going to occupy one of the common packing arrangements that we learned last time. So these larger ions are going to arrange themselves into a regular array, and the ones that we're especially going to talk about are the ones that we sort of mentioned last time. So primitive, cubic, face-centered cubic, or hexagonal cubic. There are no common ionic structures that we'll talk about that involve body-centered cubic, but these three, and especially the first two, the cubic ones, we're going to talk about in a lot of detail. So one of the ions is going to sit in those positions, either on the corners of a cube to make a primitive cubic structure, or on the corners and the faces to make a face-centered cubic structure. So that's how one of your ions is going to arrange itself. The oppositely charged ion, the smaller of the two, which is usually the positively charged one, this ion is going to occupy holes in the structure. So remember when we classified these different structures last time, we calculated the packing efficiency, and the packing efficiency was never 100%. So there's always a little bit of empty space in the structures. And essentially these smaller positively charged cations are going to sort of slide in, they're going to take up some of that empty space. So the smaller ions are going to occupy holes in the structure. And we have some predictive power over the structure. So the observed structure that we see, so again, whether the larger ion is primitive cubic or face-centered cubic, that observed structure as well as which holes are filled is going to be determined by the relative sizes of the ions. Okay? So that's going to be the one key criterion we look at to decide which structure does this compound occupy. And it's going to be the relative size of the ions. It's not a perfect prediction, so we have some guidelines in place to help us predict what the likely structure will be based on the size of the ions. It doesn't always work, but that's sort of the only prediction we really have at our disposal to be able to decide which structure an ionic compound is likely to take up. So to be able to do that, we need to know the ionic radii of both the cations and the anions in the structure, and the ratio of the two will allow us to predict which type of structure we observe. We're going to get into a little bit of that today. All right, so that's kind of the general details. So what we're going to first do is define the types of holes that we have in these structures. So as I said, we're going to put the cations or whatever the smaller ion is into holes in one of these common cubic structures that we introduced last time. So the first time is called a tetrahedral hole. And we want to think about what's the location in the structure. So the tetrahedral hole is in what we call a dimple of a cubic close-pass structure. So for a tetrahedral hole, you're going to have your anions or your larger ion, if it's the cation, but usually the anion, occupying a face-centered or cubic close-packed arrangement. And you have these little dimples in the layer. Remember that each layer has these little triangular holes in them, and you're going to slide into that gap in between in that layer and the one above it is what's called a tetrahedral hole. So it's located in a dimple of a CCP layer, cubic close-packed layer. And if the easier way to think about this is to look at the cubic unit cell and figure out where those are in the unit cell. So in a cubic unit cell, each corner of a cubic close-packed structure is going to have one of these tetrahedral holes. All right, so if we go to this little diagram here, this is a face-centered cubic lattice. So the gray ions occupy the face-centered cubic lattice. The purple ions are also part of that lattice. They're just highlighted to show where the tetrahedral hole is. So in each corner of this lattice, in between 4 adjacent ones, so 1 in the corner and then 3 on faces, so this 1, 2, 3, 4 atoms, they form a tetrahedron. In the center of that tetrahedron, this little X here, is what's called a tetrahedral hole. And there's going to be a total of 8 of those. Each corner of the cube is going to have one of those. It's inside the cube, but it's near the corner. So if you imagine dividing the cube up into 8 sort of regions, 4 on top, 4 on the bottom, each of those little cubes that you divide it into is going to have one tetrahedral hole at the center. And we call it tetrahedral hole because each one has 4 nearest neighbors that surround it that are closest to it in that structure. These are a little bit harder to visualize than the other holes, as we'll see. All right, so if we want to determine the relative size of this hole, so that's the location, they're inside the structure. As we saw earlier last time, so I'm going to do a short derivation. Again, you don't have to know these derivations. This is just for educational purposes only, which is in theory the purpose of the whole class, but these are not going to be tested on necessarily, but just to give you an idea of how we determine the relative sizes of these holes. So we saw that in a cubic close packed structure, face-centered cubic, the side length A is 2 radical 2 times R, where in this case we're going to say R is the radius of the larger ion. All right. So then as we go across a cube diagonal, or half a way to the center, so as we go from this corner to the center, 1/2 times the diagonal of the cube, that's given by a radical 3, which is 2 square root of 2 times square root of 3 times r. So that's just geometry. The diagonal, or a radical 3 over 2, I guess. Two radical 3, and then we take off, divide by 2. Okay, so that's the correct. We're going to do half a cube diagonal. It's going to be a times square root of 3 over 2, which is radical 2 times r, making this substitution. And then as we traverse across the diagonal, it's going to be, we're going to go through the radius of the large radius. We're going to go through the diameter of the second one, and then we're going to go through another corner of that small cube there. So that's equal to, I keep doing this for the whole diagonal, let's do it for one. It's going to be 2 times big R plus 2 times little r. So as we go across this diagonal, we go through the radius of the large ion, we go through the diameter of the small one that's in the center of that tetrahedral hole, and then we go through the opposite corner, which is equivalent to the radius, again, of the large ion. So that's the relationship, and what we get then is that the little radius r is equal to radical 2 radical 3 over 2 minus 1 times big R. So just some algebra to solve for the small radius here. And again, what the important thing is the number here. So this numerically equals 0.225 times the large radius. So basically what this is saying is that whatever the ionic radius of the larger ion is, the anion in most cases, the tetrahedral holes are going to be 0.225 times that radius. They're going to be 22.5% of whatever the radius of the larger one. So again, the holes are smaller than the ion itself. So that's the size of a tetrahedral hole, is 0.225 times the size of the anion that makes up the structure. Okay? So the important things, again, are locations of the tetrahedral holes in the middle of these 8 corners of the cube, in that region over there. There'll be another one up here, here, and so on. And then the sizes of those, which is 0.225 times the radius of the anion. All right, so that's the first type of hole. The second type is an octahedral hole. So there's only going to be like 3 types of holes, so don't get too concerned. There's only 3 of them. All right, so these are located between 2 sets of 3 spheres in adjacent CCP layers. So octahedral holes also occur in the cubic close packed or face-centered cubic structure. So again, thinking about the layered structures, there's going to be an octahedral hole that's in between 2 sets of 3. But the more important way to think about this is in terms of where they are in the unit cell. So in the face-centered cubic unit cell, you're going to have 1 on each edge of the unit cell. And 1 in the center of the unit cell. All right, so if we go to the face-centered cubic structure, this picture down here, the red circles are the locations of the face-centered cubic lattice. Again, 1 in each corner, 1 on the center of each faces. and these little white circles labeled with an O are the octahedral holes. So each of the edges of the cubes has an octahedral hole right in the middle of it, which would then be shared by other adjacent unit cells, and then you have one right in the center. And why we call it an octahedral hole is pretty obvious if you focus on this one in the center here. So if we look at the one on the center, it's surrounded by the 6 face atoms, making an octahedral structure like we learned about back in chapter 4. So you have 1, 2, 3, 4, 5, 6 nearest neighbor atoms that surround that center position in a face-centered cubic, making up an octahedron or octahedral structure, why we call it octahedral holes. All right. And if we want to determine the relative size of these, the side length A is equal to 2 square root of 2 times the big radius as we derived last lecture. And as we go across the side of the cube here, we go through, again, 2 radiuses of the large atom plus 2 times the radius of the smaller one. So we have those 2 radii for the large atoms plus the whole diameter of the small atom that's located in the octahedral hole. So that's going to be 2 times r, big R, plus 2 times little r, where capital R is the radius of the anions, lowercase r is the radius of the cation. So when we simplify this, we get radical 2 times big R equals big R plus little r, and then we solve for the radius of the little one, which is radical 2 minus 1 times the large radius, which is 0.414. So we derived last time that the tetrahedral holes was 0.225 times the large radius. This one is 0.414 times the large radius, so an octahedral hole is larger than a tetrahedral hole. Okay, so we now have looked at 2 types of holes that are located in a face-centered cubic structure. Tetrahedral holes located in the corners inside the cubes, octahedral holes located on the edges in the center, and the octahedral holes are larger, 41.4% of the larger radius versus the tetrahedral holes, which are 22.5% of the larger radius. Okay, so that's how big of a ion we could fit into those holes, as we'll see later on. All right, so that's the second type of hole, and then the last one is actually the simplest of them. These are called cubic holes. So in a cubic hole, we just have our anions are arranged into a simple cubic structure, and the location of the cubic hole is just right in the center of that structure. Okay, so the cubic holes are in the center of a simple cubic structure, so the easiest ones to locate. So we would have our anions on the corners, and then in the center here is the cation located in the cubic hole, right in the middle of the cube. So this time it's not a face-centered cubic arrangement of the anion, it's a simple cubic arrangement, and the one hole that we have in that structure is right in the middle, in the center of the cube. So this one, the math's a little bit easier. So as we saw last time, for a simple cubic structure, the side length A is equal to 2 times the radius. The diagonal of a cube from geometry is a square root of 3, which is equal to 2 times big R plus 2 times little r. So as we go across the diagonal, we go through the radius of the large one, we go through the diameter of the small one, and the radius of the large one to get to the other corner. So that's the relationship between cube diagonal and radius. So then we're going to replace A with 2r and get this relationship, and then solve for little r again. So again, these derivations, if you don't follow them, it's okay, but this shows where these numbers come from. So what this means is that the radius of the cubic hole is going to be 73.2 or 0.732 times the radius of the larger anion. So that's the biggest one yet. So those are the 3 types of holes we're going to talk about in the cubic structures where we can put cations when we're forming ionic compounds, and they have 3 distinct sizes. Tetrahedral holes are the smallest, octahedral holes in the middle, cubic holes are the largest. Okay, so those are the sizes and the locations of the holes. That's one thing we want to know about them. The other thing is how to count them. So when we're forming these ionic compounds, as we know, the formula of an ionic compound is going to have the correct ratio of cations and anions to balance the charge. So we need to think about how many of those holes in the structure need to be occupied by the cations to balance the charge. Is it all of them? Is it some of them? And it might depend on the formula of the compound. So when we count them, we're going to use the rules for counting that we learned last time for the different locations of a cubic structure. All right? So if we think about the tetrahedral holes, which are pictured here, these little white circles in this diagram at the top, all 8 of the tetrahedral holes, there's 8 of them, one near each corner. There's 8 corners in a cube, and each one has a tetrahedral hole located near it. But all 8 of them are completely inside the unit cell. So they're not on the edges, they're not on the sides, they're not, not in the corner, they're actually inside the cubic unit cell, so none of them are shared. So for a tetrahedral hole, all 8 of the tetrahedral holes are inside the unit cell. So that means if we were to occupy all 8 tetrahedral holes, we'd have 8 of that ion in the structure. So there's 8 tetrahedral holes. So completely filling the tetrahedral holes would result in 8 of that cation in the structure, in the unit cell. Okay? Those are all inside them, so we count them individually. They're not shared by any other adjacent unit cell. If we go to the octahedral holes, here we have to use some of the counting rules we learned last time. So as we said, the octahedral holes are located on the edges and the center. So the ones that are on the edges, how many edges are there in a cube? Almost. 8 is the top and bottom, but we have to remember the sides as well, so there's a total of 12. So 12 edges on a cube. 1, 2, 3, 4 on the top. 1, 2, 3, 4 on the bottom. 1, 2, 3, 4 on the sides. So there's a total of 12 edges in a cube. And how do we count atoms that are located at edge positions? How many are they shared with? So we learned last time how to count these. We didn't deal with edge positions much last time because they don't occur in the metallic structures, but those are shared with 4 unit cells. When you arrange all unit cells and stack them in all directions, you would have each edge is shared by 4, one beside it, and then one in front, and then the 2 in front of it as well. So you're going to have each counting as a fourth for an edge position. So those are our 12 edges, each counted as a fourth of an atom. And then we have also the one octahedral hole that's right in the center. And as we said, any atom that's in the center of the unit cell, completely enclosed by the unit cell, counts as one full atom. So you have one center position that counts as a full atom. So in total, you have 4 octahedral holes. So what that means is if we occupy all of the octahedral holes, there will be 4 of those cations in the unit cell. Okay? And then cubic holes, also from a counting standpoint, are the simplest. We have 1 cubic hole in the center. It's completely in the center of the unit cell, so it's not shared. So we just have 1 cubic hole. All right? So that's how we count them. And that means if you have the cubic hole occupied, you have 1 cation in that unit cell. All right, so we now know the locations of the holes, we know the sizes, and we know how many of them there are in the structure. So let's do a quick summary of that here, because this again is the important information you're going to want to know about these when you're going through homework and test questions. So we have tetrahedral, octahedral, and cubic. The tetrahedral holes, as we just counted, there's 8 of them in one unit cell. Octahedral has 4, cubic has 1. So that's the number of each per unit cell. And then what we're also going to talk about, and we sort of saw it a little bit when we derived the sizes of these, is what's the size of the smaller ion, usually the cation, that can occupy one of those holes. And this is how we predict which of the holes will be occupied. So we saw that for the tetrahedral holes, their size in a cubic close-packed structure is 0.225 times the radius of the larger ion. We saw that the size of the octahedral hole was 0.414 times the radius of the larger. And then we saw the cubic hole was 0.732. So that's the size of each hole that we derived using geometry. I went through it really quickly, so likely didn't follow all the details. But using geometry, just the diagonals of cubes and some of the relationships involving the atomic radius that we talked about last time, we derived these sizes. Now these are the limiting sizes. So what if it's in between one of these numbers, right? So basically the tetrahedral hole is going to be occupied anytime the cation is between 0.225 and 0.414. So basically the structure can expand a little bit to accommodate a slightly larger cation than that. So if the size of the cation is between 0.225 R to 0.414 R, So that's, again, the relative radii of the two ions. This being the smaller one is either 0.225 times the larger one or up to 4.414. It's going to occupy the tetrahedral hole. That's the prediction we would make. So again, those are limiting values. If the size of the smaller ion is 0.414 or larger, up to 0.732, it's going to occupy octahedral holes. So again, these are always ranges that we would predict. So if the size of the smaller ion is in that range of relative radius of the larger one, it's going to occupy an octahedral hole, or at least that's the prediction we would make. As I said, these predictions are not perfect, but they're pretty good guidelines. And then finally, for cubic holes, anytime the radius of the smaller ion is greater than 0.732 times the radius of the larger, then we would predict cubic holes being occupied. So again, using the relative radii of the two ions, smaller divided by larger, we can predict which type of structure these will occupy and whether the cations or the smaller ion would go into the tetrahedral, octahedral, or cubic hole. Okay? So we'll give some examples of that in real structures later on to show how that analysis is done. And then finally, remember, we have to think about what unit cell does the larger ion occupy? What kind of unit cell do we need for these holes to exist? So the tetrahedral and octahedral holes are located in the face-centered cubic structure, or cubic close packed is the synonym of that. So in both of these, the anion would occupy the face-centered cubic structure. For the cubic holes, these occur in the primitive cubic structure. Okay? So those are the really only three types of ionic structures that you would need to know anything about. Face-centered cubic with either tetrahedral or octahedral holes occupied, or primitive cubic with cubic hole occupied. So that's kind of the summary of the main things you need to know. Now we can go through a few examples. Before I go through some example structures, any questions on this? Yeah. Well, yeah, it would go up to basically if the two are equal. So they're going to, the largest ratio would be 1 for smallest over largest. So anything up to where the two ions are equal in size, which rarely occurs but could be the case, anything up to that you would occupy the cubic hole. It's not going to be bigger than 1 because we're always dividing the smaller by the larger. So some ratio between 0 and 1. So up to 1 would give you a cubic hole. All right, any other questions? Yeah. Trigonal holes? No, I don't think so. So that's not going to be one you're going to be responsible for directly. We might give you problems about it, but we will give you enough information in the problem for you to know where those are located and how many there are. Okay? Any other questions? All right. So then moving on to some examples of ionic structures. So we can use the analysis, some of the features we just talked about to predict. So let's say we have sodium chloride, world's most common, one of the simplest ionic compounds. So to predict what structure this ionic compound takes up, we're going to look at the ionic radii of the two sodium and chloride in the structure. Okay? So these are just tabulated values. You can't calculate these or predict these in any way. We can predict the relative size. We should know that sodium is much smaller than chloride because sodium is in the valence electrons. Let's review that quickly so I'm not just saying it. So we can predict that sodium is smaller than chloride because sodium has the electronic structure of neon, so it has 10 electrons total. Chloride has the electronic configuration of argon, so we would predict that chloride is larger than sodium, right, on the basis of periodic trends that we learned a long time ago. So we know that the anion is larger than the cation, as is usually the case. The exact sizes of those would be, again, values that we'd have to give you. So the radius of a sodium cation is 102 picometers, and the radius of the chloride anion is 181. So quite a big difference between those. All right, so those are the values, sorry, not ppm, just pm, picometers. All right, so those are the values of the ionic radii for sodium plus and Cl minus, the two ions that make up this ionic compound. So then if we want to decide which holes are filled, we have to take the ratio of the two. So we take the ratio of the smaller ion, which is the cation in this case and in most cases, divided by the radius of the anion, which I previously abbreviated as big R. So these are just the two ionic radii divided by each other. So when we take 102 divided by 181, we get a ratio of 0.56. And as we just talked about, if the radius is between 0.414 and 0.732, if that ratio is between 0.414 and 0.732, that's going to lead to the prediction of occupying the octahedral holes. All right, so this is the intermediate size of the ratio. All right, so if it's smaller than 0.414, we would expect it to be tetrahedral holes. If it's between these two values, we expect octahedral holes to be occupied. So that's what we predict. Now we want to think about how many of these holes are actually filled. So we have to think about how many of each ion would be present in the structure. So our chloride is going to occupy the face-centered cubic lattice. Okay, so remember the larger ion, in this case the Cl-, is going to occupy the positions of the face-centered cubic lattice whenever we want to fill octahedral holes. So that's the green ones here, the typical face-centered cubic arrangement that we talked about last time. And last time we also talked about how to count the ions in a face-centered cubic structure. So in the face-centered cubic lattice, you have 8 corners, and each of those counts as 1/8, because they're shared by 8 adjacent unit cells. We also have 6 faces occupied, and those each count as 1/2. So there's going to be a total of 4 Cl- in the structure. So that's how many chlorides are in the structure, because all the face-centered cubic positions are occupied. If we have octahedral holes being filled with the cations, as we saw in the last couple slides, we have 12 edges that are going to contain octahedral holes that count as a quarter, plus the one in the center. So we have 4 octahedral holes. So if we have 4 octahedral holes, how many of them do we need to fill? Do we need to fill all 4 of them or just some of them? Someone said all 4, which I agree with, because we want the number of cations and anions to be equal. The formula of the compound is NaCl. You need equal numbers of cations and anions. So if our unit cell has 4 chlorides, it better also have 4 sodium ions to balance the charge. So that means we're going to fill all 4 holes. And by doing so, we would have 4 of each, sodium 4, Cl4 for each unit cell, which the empirical formula would still be, of course, sodium chloride, NaCl. Okay, so you need to make sure that you have the correct ratio of cations and anions in your structure. For sodium chloride, it needs to be a 1-to-1 ratio. So face-centered cubic gives us 4 anions, which means we also need to have 4 cations, meaning all 4 octahedral holes would need to be filled. All right. One thing we haven't talked about is coordination number, but the coordination number is typically for the cation in the structure. The octahedral hole has a coordination number of, what does octahedral mean in the context of molecular geometry that we learned last time in chapter 4 earlier. How many electron groups gives us octahedral? 6. So the coordination number for an octahedral hole is 6. Right? So that's the same definition. And again, if we focus on the center one here, you have 1, 2, 3, 4, 5, 6 nearest neighbors. That gives us a coordination number of 6 for each octahedral hole. Okay, so that's the coordination number of the sodium, meaning each sodium ion is surrounded by 6 chlorides in this structure. Okay, the one in the center would be nearest to the ones on the 6 faces that are surrounding it. All right, so that's some features of the sodium chloride structure, where again we can use the relative radii to predict which of the holes is occupied. And so this diagram here shows us the full sodium chloride structure. Green is the chloride anions located on the face-centered cubic positions. Orange is the sodium cations located on the octahedral holes, the edges, and the one in the center. And that's what the structure of sodium chloride would then look like. Okay? Let's go to a different one, cesium chloride. So still an alkali metal chloride, but now we're replacing the sodium cation with cesium plus. So we're just moving down the periodic table. So if we look at the radii this time, we have cesium plus, which has a radius of 174, and Cl-, same anion, still has a radius of 181. So we have different cations, same anion. So to figure out which holes are filled, we once again take the ratio of the cation to the anion, the smaller to the bigger in this case. And this time they're very similar to each other. So 174 divided by 181 is very close to 1, 0.96. So as we said, if the little radius is greater than 0.732 times the larger, that's going to lead to the prediction that we're going to occupy a cubic hole. Okay? So we have a radius ratio that's greater than 0.732. That's the largest of the holes that we need to occupy, which is the cubic hole. So the cubic hole is going to involve the simple cubic lattice for the anion. So in this case, the chloride anions are going to be in a simple cubic arrangement, and those just occupy the corners. So in this structure, the chloride ions occupy the 8 corners, which each count as 1/8. So in net, there's 1 chloride ion per unit cell. And then how many cubic holes are there per unit cell? There's the 1 cubic hole in the center, which counts as a full atom, so that's 1 cubic hole. So once again, all cubic holes are filled. So by filling the 1 cubic hole, we get a total of 1 chloride and 1 cesium, balancing the charge, making the formula correct, cesium chloride. And then the coordination number for a cubic hole is, again, pretty easy to visualize from this structure. We have a cubic hole right in the center. How many nearest neighbor atoms does this have? 8. All 8 corners are equidistant from the center of this cube, so you have 8 corners, 8 corner atoms that are going to be surrounding that. So the coordination number for a cubic hole is going to be 8. So that's something we didn't talk about in that table, but you have also a coordination number associated with each of these structures as well, which is 8 for the cubic holes. Okay? Any questions so far? All right, the last example structure we'll give you is going to be zinc sulfide, ZnS. All right, so once again, we're going to look at the ionic radii to be able to make some predictions about the structure. So the zinc 2 plus cation has a radius of 60 picometers, and the S2 minus anion has a radius of 184 picometers, very similar to the chloride anion that we saw earlier. They have the same number of electrons, a little bit bigger, as we would predict. So radius of the two the cation and the anion. So to predict which holes are filled, we take the ratio of the two, smaller over larger, which comes out to 0.33. All right? And what we just learned a little bit ago is that if the small radius is between 0.225 and 0.414 times the larger radius, which holes do we predict will be occupied? These are the tetrahedral holes, that's correct. So those are the smallest of the 3 that we talked about. So in this case, you have to go into the tetrahedral holes. So because we're occupying tetrahedral holes, that means our anion, the larger ion, has to occupy, again, the face-centered cubic lattice. So tetrahedral holes only occur in the face-centered cubic structure. So we have a face-centered cubic arrangement of our sulfide ions, and as we already counted a couple slides ago, that means we have 4 sulfide anions in the structure when they're occupying these yellow ones here are the sulfides. And then when we count tetrahedral holes, how many of those are there? So there's 8 tetrahedral holes. All 8 of them are inside the unit cell. So how many tetrahedral holes in total are there in that? 8. Okay? So we have 8 tetrahedral holes, and which means if we put cations in all 8 of these, we would have 2 zinc atoms for every sulfur, 2 zinc ions for every sulfide, which is the wrong ratio. We only want to have 4 zincs, so we can't fill all 8 tetrahedral holes. We're only going to fill half of them. All right, the reason for this is if we filled all 8 tetrahedral holes, we would have 8 zincs in the structure, and we only have 4 sulfides because that's in the face-centered cubic position. So we would get Zn8S4, which reduces down to Zn2S, which is the wrong formula. The formula for zinc sulfide is just ZnS, 1 of each, 1-to-1 ratio. So we can only fill half the tetrahedral holes because if all are filled, we would get the wrong formula. Half are filled, and that gives us zinc 4S4, which reduces to zinc sulfide. Okay, 4 of each, which means they're in the 1-to-1 ratio. So this is the first one we saw where we're not going to occupy all the holes, but half of them. And this is the structure we get. We get alternating tetrahedral holes that are occupied. So 2 on the top, which are shown in purple here, 2 on the bottom, also shown in purple, that are sort of alternating. So these 2 kind of go in this direction, these 2 go sort of back in the other direction, and they are alternating tetrahedral holes that are occupied, but not all 8 of them. So there's going to be a tetrahedral hole over here that's not occupied, one over here that's not occupied, a little bit hard to draw, one up in this corner, and one up in this corner here in front of that. So there's 4 tetrahedral holes that are empty in this case as well. And then the coordination number for a tetrahedral hole, again, comes directly from the name. So as we learned in Chapter 4, if you have a tetrahedral geometry, how many things are bonded to the central atom? What's the steric number for tetrahedral? All right, seems like we need to review chapter 4 before the final. Coordination number will be 4 for that. Okay, so when you have a tetrahedral geometry, that means there's 4 things bonded to your central atom. So if we look at each zinc in this structure here, you have 1, 2, 3, 4 sulfurs that surround it. 1 from the corner that it's in, and then 3 from the adjacent faces that it's closest to, total of 4. Okay, and that's the coordination number for a tetrahedral hole in a structure. All right, so any questions on these 3 structures? Again, these are just examples to show how we can use radius ratios to predict, and how we have to sometimes use the formula of the compound to predict whether we fill all or just some of the holes. Okay, any questions on that? All right, so let's look at a couple of example problems that you might see similar ones on homework assignments or exams. So let's go to the calcium fluoride structure now. In calcium fluoride, the cations occupied a face-centered cubic array. The anions fill the tetrahedral holes. So here we're telling you that directly, that they're filling the tetrahedral holes. How many of them must be filled? So similar analysis that we've been doing for the last 3. So what's the formula for calcium fluoride? We need to think about that first. Calcium has what charge? 2+. Fluoride has what charge? 1-. So if it's a 2+ cation and a 1- anion, the correct formula would be what? CaF2. So that's the formula of the compound here. So we're going to count each of the ions. So here we're saying that the cations occupy the face-centered cubic array. So this is a little bit opposite of what we normally see, but we're telling you that here directly. So the number of calcium cations is going to be, those are occupying the face-centered cubic positions. So remember, in face-centered cubic, you have 8 corners filled, each counting as an 1/8. So that's the corner positions. You have 6 faces occupied, each counting as a 1/2. So in total, we have 4 calcium ions in the structure. The number of tetrahedral holes in the structure is how many? We just saw this in the last one. 8. 4 was half of them. There's a total of 8 if we filled all of them. So if we have 4 calciums, that's fixed by the face-centered cubic arrangement of them. How many fluorides do we need to balance charge? The CaF2. So if we have 4 calciums, how many fluorides do we have? So that means we need to fill all 8 of the tetrahedral holes to have the right number of cations and anions. So in this structure, because we have a 1-to-2 ratio of cation to anion, if we put the cations on the face-centered cubic positions, our anions would need to occupy all 8 of the tetrahedral holes to be able to balance the charge correctly. So face-centered cubic gives us 4 calciums. We need to have 8 fluorides to give this the correct empirical formula. So all 8 tetrahedral holes have to be filled in this structure. So this structure would look a lot like the last one, except that now all 8 of the holes, the other 4 that are empty here, would include anions in this case. All right? Any questions on that? All right, and then this one is a weird one. So this is not one of our sort of normal ionic structures, but again, we give you enough information here to figure it out. So we have a compound called lithium boride. This is sort of remember boron is a metalloid, so this is sort of in between an ionic compound or what we would call a either a, what do they call those? A binary phase or a intermetallic, they're sometimes called, kind of like an alloy. So again, boron is a metalloid, so whether you count this as an ionic compound or as an alloy is kind of ambiguous. That's not the point, though. So the point is that it's a binary compound that consists of lithium and boron, as the name implies. So we're giving you here the structure information. The boron ions occupy a face-centered cubic lattice. The lithium ions occupy the octahedral and tetrahedral holes. So what is the formula for this compound? So here again, we're telling you the structure. We just have to use the structure to predict the formula of the compound. All right, so if boron occupies the face-centered cubic position, we've said many times already how many boron ions would that correspond to if it's occupying a face-centered cubic lattice? 4. Right? 8 corners, 6 faces, and that's 4 ions. We have 4 borons in the unit cell. And then for the lithium, as we said in this compound, which is not the most common situation, but it occurs here, we have octahedral holes and tetrahedral holes occupied. So both of those are going to be filled. So the octahedral holes, as we've seen and is summarized in the table that I gave you earlier, There's a total of 4 octahedral holes, 12 on the edge plus the one in the center gives us a net of 4. And as we've seen many times already, there are 8 tetrahedral holes. So if all of those are filled with lithium ions, we're going to have a total of 12 of those. So that means in total what we have is 12 lithiums and 4 borons, and as we would do for any ionic compound or any intermetallic, if you want to call it that, in this case, we reduce it to the empirical formula, which is going to be Li3b. Okay? So in this structure, you can almost think of boron as behaving like a 3- anion, paired with 3 lithium plus cations. All right? It's again, maybe not quite that cut and dry for this one because boron's a metalloid, but we can use the information on this to get the formula. So any questions on that one? All right, so that takes care of ionic structures. The next topic we're going to go do is now back with liquids. So we're going to talk about a few more things related to phase changes, especially those that involve liquids, to sort of close things out. All right, so we're going to talk about vapor pressure in more detail. We introduced vapor pressure in Chapter 8, as we saw in some of those problems where you have to collect gas over water. You have vapor pressure of water that contributes to the total pressure that you observe. So we kind of introduced that at a very basic level. Now we're going to talk about in more details what causes vapor pressure, what are some of the factors that influence vapor pressure, and a couple little calculations involving it as well. All right, so we're going to talk about vaporization. We're going to introduce that definition first, and that's the process of converting a liquid to a gas. So we did introduce phase changes at the very beginning to sort of prime you for a lot of things we're talking about in this chapter. And the process of converting a liquid to a gas is called vaporization. We sort of colloquially refer to it as boiling also, but boiling has a more specific definition that we'll get to later. Vaporization is any time a liquid goes to a gas, anytime you have that phase change from liquid to gas. So vaporization, or any phase change, as we're going to talk about, has an enthalpy change associated with it. So we're going to abbreviate this as delta H of vaporization, delta H VAP for vaporization. So that's the enthalpy of vaporization. And this is the enthalpy change associated with vaporizing 1 mole of substance. So vaporization is technically a physical process, but it would still have an enthalpy change associated with it. So that's what that delta H vaporization refers to. All right, so what do we think? Is vaporization enthalpy going to be endothermic or exothermic? There's a lot of X's, which is sad. All right, so let's think about it in more detail. So if you want to take a substance and go from liquid to gas, do you have to put heat into it, or do you have to take heat out of it? Put heat into it. Remember, if we put heat into the system, that's an endothermic process. So delta H vaporization will always be endothermic. Remember, vaporization and boiling are kind of related to each other, as we'll see later. So if you want to boil something, you put energy into it. And similarly, if you want to vaporize something, you have to put heat into it to cause it to vaporize. Remember, in the context of intermolecular forces, you have intermolecular forces that are holding a liquid together, dipole, hydrogen bonds, whatever the case is. If you want to vaporize a substance, you have to break those intermolecular forces and separate the molecules, so you have to put energy into it to break those forces of attraction. So delta H of vaporization will always be endothermic, meaning that value will always be positive. Condensation is then the reverse process. So if we go from gas to liquid, that's called condensation. So that's when molecules in the gas phase become liquid. And the delta H for condensation is just the negative of the delta H vaporization. So these two processes are exactly opposites of each other, so the delta H, you just take the negative of it, so it'll always be exothermic for condensation, okay? And that you can also rationalize from your everyday life. So if you have a pot of boiling water with steam coming off of it, the steam is water vapor. If you hold your hand above that and let the water vapor condense on your hand, does that feel hot or cold? hot. Please don't do it for too long. And so that, again, verifies that that's an exothermic process. When something condenses, it transfers heat to the surroundings, making it exothermic. You can also, again, see that because vaporization is endothermic, the opposite process would be exothermic. Okay? So those are the phase changes associated with vaporization and condensation, two reverse processes involving interconversions of liquids and gases. Now we can start talking about a little more detail what causes vapor pressure. All right? So we're going to talk about this sort of in words and in pictures. So if we put a sample of liquid into a closed container, so we have liquid in a closed container here. This is the beginning when we first put the liquid in. So at the beginning of this, when we first place the liquid into the container, there is net vaporization as surface molecules escape. All right, so initially when we put a liquid into a closed container, there's going to be some of the molecules at the surface that are going to vaporize. So some of these surface molecules are going to go up into the vapor phase, and that's going to cause a vapor pressure to start developing. However, at some point, we're going to have an equilibrium established. So eventually, put that in the next line. So eventually what's going to happen is you're going to get to a constant vapor pressure. So initially the vapor pressure is going to increase as more and more molecules escape into the vapor phase, but then at some point you're going to get to a constant vapor pressure that you're going to establish. And the reason for that is if we look at the picture of sort of the end point, or equilibrium point as you might want to call it, where the vapor pressure is now constant, what's happening is that we still have molecules escaping into the gas phase, but now molecules that are already in the gas phase are going to start recondensing. So you have sort of this dynamic process where you're going to constantly have some molecules going into the gas phase, other molecules condensing, and it's sort of this back and forth process where in that you no longer have any increase in vapor pressure. So you're going to have vapor pressure caused by the molecules that are in the gas phase, but at some point, you're going to get to a situation where the rate of evaporation and the rate of condensation are the same, and so in that you have the same number of molecules in the gas phase at all times, and the vapor pressure stays constant. So graphically, what this looks like is over time, I'm going to show the vaporization rate in blue. So the vaporization rate is constant, which means as long as you're keeping the temperature same, the rate of vaporization is going to be a constant, shown in blue here. But the condensation rate is going to increase and then get to some steady value. And then it's going to get to some stable value where the two are equal. So blue is going to be vaporization, which is a constant rate, doesn't change over time. And then red is condensation, because remember at the beginning there are no molecules in the gas phase, so if there's no water vapor you can't have condensation, but then as you start to get water molecules in the gas phase, some of them are going to start condensing back, so the rate of condensation is going to increase until eventually they're both equal and constant. Okay? So again, at some point in time you're going to get equal rates of vaporization and condensation, and you're going to have a constant vapor pressure as a result. Okay? So eventually the vapor pressure will be constant. It's not going to change over time. It's going to get to a steady state value. Okay, so that's kind of a sort of a molecular level picture of why vapor pressure even occurs at all. To think about this in a little bit more detail, we can talk about how to measure vapor pressure. This is just a little bit of background that's probably not terribly important. But to measure vapor pressure, we're going to first measure the atmospheric pressure with a barometer. All right, so remember that a barometer, a simple design for a barometer is you have a dish of mercury and you invert a hollow tube into it. So this is my barometer here. And you measure the height of this to tell you what the atmospheric pressure is, because you have atmospheric pressure pushing down on the surface of the mercury, which forces some of it up into the tube, and the height of that gives you your atmospheric pressure, which at sea level is around 760 millimeters. Okay, so that's just a barometer. And this top part of the barometer here initially is a vacuum, so there's no air up there. It's just a vacuum. All right, so that's what a barometer looks like. And then what we're going to do is then we're going to inject a liquid into the top of the barometer. So we're going to add a liquid to that top section, the headspace as we call it. So again, this little top part here that's just filled with vacuum, we're going to put some of our liquid into it. And so when you have that, what's going to look like now is you have the same barometer. You still have atmospheric pressure pushing down. I want to enlarge this a little bit so we can see it actually. And what you also have then is the vapor pressure opposing that. So our vapor pressure here. Because when we inject the liquid in the top part, there's going to be some vapor from that liquid that's going to push down on the mercury, and you're going to have sort of this decrease in the height. And so you have a new height here, H, that's going to be different than the initial because you have vapor pressure that opposes your atmospheric pressure. So if we assume the atmospheric pressure is 760 millimeters, the height that we observe here is going to be the atmospheric pressure, the difference between the atmospheric minus the vapor pressure. So the new observed height is going to be the difference between the two. So for water at 25 degrees Celsius, we would observe a height of 736 millimeters when we put water into the top part of the barometer. And that means the vapor pressure for water would be 760 millimeters of mercury, which is the atmospheric pressure, minus the new observed height of our barometer, which is 736, which is 24 millimeters of mercury. So this gives you a little bit of background of how we measure the values of vapor pressure. We would inject a liquid into the top part of a barometer. I enlarge it over here so you can see a little bit better what's happening, and then you have vapor in the top part of the barometer now, no longer just pure vacuum. That vapor is going to push down on the column, which is opposing the pressure from the atmosphere. And then you're going to have sort of this difference between the two is that new height. Okay? So that's how we measure it. It's just related to the principles of a barometer that we learned back in Chapter 8. Now the next thing we're talking about is going to be the temperature dependence of vapor pressure. All right, so we saw that in the previous example where I gave you the vapor pressure of water at 25 degrees Celsius. But what if the temperature is different than 25 degrees Celsius? How does that affect things? So if we think about a sample of a liquid, we saw for gases that all gases have a distribution of molecular speeds. And the same is true, or kinetic energy, I guess is another way to say it. The same is also true for liquids. So we don't have as simple relationships. We talked about the relationship between temperature and molecular velocity, kinetic energy for gases in Chapter 8. Similar things happen for water, although they're more complicated, but still there's the same trend. If you increase the temperature of a sample of liquid, you're going to have an increase in the average kinetic energy. So at some temperature, which I'll call our cold temperature, you're going to have a distribution of kinetic energies. So there's always a distribution even in a sample of liquid. They don't all have the same kinetic energy. Some have lower, some have higher, and there's this sort of average value here that's characteristic for that temperature. And then in the liquid, some fraction of these, let's say this fraction here. So some kinetic energy is required for the liquid to escape the surface of the gas. So basically the kinetic energy of the liquid has to be great enough to be able to break the intermolecular forces and escape from the surface to be able to go to the vapor phase to create vapor pressure. So at this temperature, let's say this is the threshold kinetic energy that you need to escape the surface. This fraction of molecules are going to have enough kinetic energy to escape. So at the first temperature, this small fraction is going to have enough kinetic energy to escape into the gas phase, and that's going to result in the vapor pressure that you measure. Now, if we go to a higher temperature, what we're going to see is that the distribution is going to broaden as it does for a gas, and it's going to shift to a higher value. So as we increase the temperature, we increase the average kinetic energy. And so if our threshold kinetic energy is located here, what we see is that we have a much larger fraction of molecules that have enough kinetic energy to escape. Okay? So this fraction of molecule has enough kinetic energy to escape now. So as we increase, let's label these appropriately first. So as we increase the temperature, more and more molecules have enough kinetic energy to escape into the vapor phase. So what do we think then happens to the vapor pressure as we increase the temperature? It's going to increase because we're getting more and more molecules into the gas phase. The more moles of gas we have, the higher the pressure will be. Okay? So vapor pressure is going to increase with temperature. That's sort of the conclusion, the qualitative conclusion we can draw from this discussion. Let's just say it more clearly than this. Vapor pressure increases as the temperature increases. All right, so this is going to be true for any substance. As you increase the vapor pressure, as you increase the temperature, the vapor pressure increases. Okay? All right, so that's the relationship, and it's again because we're changing the distribution of kinetic energies, the distribution of molecular speed. At the higher temperature, more molecules can escape the surface and get into the gas phase. All right, so the equation for this then, which we're not going to derive in any way, is going to be shown here. Okay, so it's a logarithmic equation. So for the first time this semester, we have to deal with natural logs. So again, make sure you know how to do that in your calculator. I think we will use this equation in some of the homework questions, so you'll want to get used to it. But anyway, the natural log of the vapor pressure is equal to the negative of the enthalpy of vaporization divided by the universal gas constant R times 1 over the temperature. Okay, so it's not a simple linear increase. Vapor pressure is not linearly dependent on temperature. It's this sort of logarithmic relationship that we're showing here, plus a constant. So this constant C depends on the identity of the substance. So it's different for every substance. Now, because this substance C this constant C is substance dependent, it's not the easiest thing to measure. It's not really widely tabulated for a lot of substances. We don't usually use this form of the equation. What we usually do is we compare two vapor pressures at two different temperatures, and we get an equation that looks like this. So it's going to be the natural log of P1 over P2 is equal to minus delta H of vaporization over R times 1 over T2 minus 1 over T1. There's a couple of different forms of this equation depending on where you put the minus sign, either in here or you can reverse the two temperatures in here and leave the minus sign off of that. So you might see it look a little bit different, but this form of the equation works. So again, two different vapor pressures, two different corresponding temperatures, and this allows us to then compare those two. All right. So in this, the temperature has to be in Kelvin, and the value of R that we want to use is the 8.314. Because this, again, is an energy equation dealing with delta H of vaporization, which is an enthalpy change. So you have to use the value of R that's 8.314, because your delta H is going to be in joules, so you want the value of R that's also in joules. Okay? So that's the value of R we want to use. There's two values of R, as we said, with two different units. So there is a linear relationship, which is kind of where this equation comes from and why it's also useful. So if we plot on the y-axis the natural log of the vapor pressure, and on the x-axis we plot 1 over the temperature, we see from this equation up here that we have y is equal to a negative constant times x. So if the constant up front, delta H vaporization is always positive, the negative sign up front makes this whole term negative. So that means this is going to be a linear equation with the slope equal to minus delta H over R, which is a negative number, and an intercept equal to that constant C that we saw in the first form of the equation. Okay? So this is one way that we can measure the delta H of vaporization for a constant. Delta H of vaporization, I should say, for this one here. All right, so if we have water, for example, which has a large delta H of vaporization, it's going to have a very large slope like this. If we look at another substance, diethyl ether, actually let's do a simpler one than that. So water has what kind of intermolecular forces? A lot of mumbling, and I think I heard hydrogen bonding in there somewhere. Okay, so water has hydrogen bonding, which is a pretty strong intermolecular force. So that means it has a pretty high enthalpy of vaporization. Those two are directly related to each other. If we go to pentane, what kind of intermolecular forces are present in any hydrocarbon? Just London dispersion forces, which are most weaker. So pentane would have a lower enthalpy of vaporization, which means the slope of its plot would be smaller. So this would be something like pentane, which has a smaller slope. So basically, the magnitude of the slope is always negative, but the magnitude of the slope is related to the size of delta H of vaporization. And enthalpy of vaporization is larger when you have stronger intermolecular forces. All right? So that's one form of the vapor pressure equation. Let's just do a quick example with it to close out. So we have diethyl ether has a delta H of vaporization of 29.1 kilojoules and a vapor pressure of 0.703 atmospheres at 25 degrees Celsius. What is this vapor pressure at 95 Celsius? So we're going to use the vapor pressure equation. Because we have two pressures and two temperatures, we're going to use this form, which is the more useful form, because we don't have to consider that constant C. I hope I did this right. T2. See, I always screw this up. There's two forms of this equation, and I always mix them up in my head. Now my tablet's frozen, so good. P1 over P2. God, I hope I didn't screw that equation up. Sorry, there is no negative sign here, my bad. All right, take that minus sign out. I apologize for that. That's what wasn't matching up. All right, so anyway, here's the correct form of the equation. Delta H of vaporization over R times 1 over T2 minus 1 over T1. As I said, sometimes the equation, you move the negative sign out front. Sometimes you don't, and you switch these. So there's two forms of the equation that I got tripped on. All right, so this is the equation. T1 is our first temperature, which is 298 Kelvin. We have to do this in Kelvin. 25 Celsius is 298 Kelvin. The second temperature that we're comparing it to is 95 degrees Celsius, which converts to 368 Kelvin. And the first vapor pressure at the first temperature is 0.703 atmospheres. Our pressure can be any units we want because this equation has a ratio of 2 pressure, so the units don't matter for pressure. All right, so that's what we're given, and we're going to just solve then for P2, which is the vapor pressure at the second temperature, T2. All right, so we put numbers in. Natural log of 0.703 atmospheres divided by P2, which is our unknown, is equal to enthalpy of vaporization over R. Delta H of vaporization is 29.1 kilojoules per mole, but we need to convert it to joules because we're going to use the value of R that's in joules as well. So our delta H has to be 29,100 kilojoules. We just take that number, multiply it by 1,000, joules per mole, divided by R, which is 8.314 joules per k-mole. All right, so again, writing out units is helpful. This shows us that both of these need to be in joules so that that cancels out. You can't leave the delta H in kilojoules or the units won't cancel out properly. So we have to make sure we remember to do that. And then the two temperatures are T1 over T2. T2 is the higher temperature, 368. And then 1 over T1, which is 298. All right, so numerically what we get is on the right side of the equation, these are all numbers, so we get minus 2.234. So we have a natural log on the left side, we have a number on the right. How do we get rid of a natural log? We use the E, right? The E to that power. So E to the natural log of 0.703 over P2, that gets rid of the natural log, so we get 0.703 over P2 is equal to e to this power here, the number on the right side of the equation, okay? Minus 2.234. So you're going to have to learn a little bit of, refresh yourself on some algebra that you should have learned a while ago in math class, as well as some calculator functions that we haven't used yet. And then numerically, e to the minus 2.234 is 0.107. When we solve for P2, we get 6.56 atmospheres. All right, so as expected, the temperature increased from 298 to 368, which means the pressure increases from 0.703 to 6.5, the vapor pressure of that liquid, as we expect. All right, so that's just a numerical example of how to use that equation. Next time, we'll see one other application of this equation related to boiling point, and then we'll move on to the very last topics that we'll cover in this course.